So let's start our discussion about short channel effectors, which is a well-known phenomena occurring in MOSFETs. Okay, so we know in our MOSFETs the basic requirement is, in fact, a trending requirement is to increase the speed. Okay, increase the speed of the device, and the main characteristic of this speed, it is basically the capacitance. Okay, so capacitance is there, which basically what I would say, which basically which basically impedes the speed. Okay, so in that way we do have a capacitance, a very important parameter to determine the speed of the device. Okay, and in fact when we say about capacitance, it depends on the channel parameters. Okay, it depends on the channel parameters, or we say in the holistic way, it depends on the size of the transistor. Okay, size of the transistor. Well, an important parameter of the size of the transistor, it is basically the length of the channel. Okay, so length of the channel. So this would be an important parameter to determine the speed of the transistor. Okay, so it would be modeled in the different ways, and we'll be seeing that how it would be able to create some extraordinary effects there in our MOSFET transistor. Okay, so when we talk about this length, and when we are just trying to scale it down just to improve the speed. Okay, so in that way we are seeing some extraordinary phenomena occurring there in the MOSFET characteristics. Okay, and in fact in its operation, those effects are called the short channel effects. And some well-known short channel effects are, the first one is double. Okay, then we do have a velocity saturation. Okay, then after we do have impact ionization, and then we do have a hot carrier injection. Okay, so these are some well-known effects caused by these short channel. Okay, short channel basically means the channel that's been scaled down. Okay, so that's been scaled down to a very lowest possible value of this channel. Okay, so let's talk about this double. Basically means drain induced barrier lowering. Okay, so what does this mean, drain induced barrier lowering? We know in case of our MOSFET, the main barrier, okay, when we talk about the barrier, it's that threshold voltage, okay, VTH. It's that barrier that's basically we would have to cross over. Okay, so as to get our MOSFET in the operation. You might be also having the idea of the diodes. How do we use there the concept of the barrier? In the very similar way it's been interpreted here. Okay, so this barrier is getting reduced, so that means VTH is getting reduced when there is been some drain. Okay, when there has been some drain related phenomena. So it's basically drain is causing this VTH to decrease. And how it's going to decrease this VTH, we'll be saying it. Okay, for consider here, this is the drain layout. Okay, and drain for an N MOSFET, it consists of N-type doping. Okay, so here the P channel, let's talk about enhancement type. Okay, so it's been it consists of some light P dopants. Okay, so now what we would have here in this region would have basically a space charge region or a depletion region. So in that way here would be a lot of little negative charge, because we see it's been heavily doped. So the depletion layer would be basically covering the it would be basically scattered over this channel region. Okay, so here would be a lot of what I could say negative charge. Okay, so here would be this negative charge, and here would be little positive charge. So it would be basically this depletion region. So this is the depletion region here formed. Okay, now it's basically the channel. Here a part of the channel would be depleted and a part of the bulk substrate would be depleted. But when our channel is small and it is going to make this channel depleted, okay, it's going to make this channel depleted. So due to this depletion, what's going on, whenever we are talking about MOSFET operation, okay, MOSFET operation, we are discussing there three things. One is called as accumulation, then depletion, and then the third one is inversion. Okay, so the threshold voltage that we are basically applying, okay, it's just to do all the three things in a very sequential way. So one of the important step is depletion. So it is depleting the channel. Okay, so it is depleting the channel. So when we see that the part of the channel is being depleted by this drain, okay, part of the channel is being depleted by this drain, that means the barrier that we were the barrier that we had been in the need to cause this channel to get depleted, that's been lowered by this drain while it is just depleting a part of this channel. For the longer channels, obviously this phenomena would not be so much sound, because channel would be long, and the extent up to which this drain would be just depleting the region, it would be quite smaller, okay, compared to the length of the channel. But when it would be a short channel, okay, of the order of nanometers or some micrometers, then this effect would have definitely a big influence, okay. So this is called a drain induced barrier lowering. That means the threshold voltage is been decreased, and that's been decreased just because of this drain, okay. So this is called a double, and it's one of the common short channel effect. Then the second one is velocity saturation. Velocity saturation is achieved whenever we do have a high field, okay. What's going on when we talk about this high electric field? That's the voltage that's been applied there between the drain and source, okay. So there is a very high electric field between drain and source, okay. This is drain and source, so here is a very high electric field. So due to this high electric field and simultaneously of the short channel, okay, the electrons are being drifted with a very high speed, and ultimately it reaches a saturated value, okay. It saturates the velocity of the electrons or the carriers saturates, okay, and that's called a velocity saturation, okay. So then after another one is here impact ionization. Impact ionization, I would be just taking it in a very quick way now. So this is basically our source, this is here drain, so it is a short channel, that means the electric field is very high. Why electric field is very high? Electric field is given by dV by dx, that is the gradient of the potential, okay. So when this dx is quite small, the channel is quite small, okay, this electric field would be high, okay. So when this electric field is quite higher, what would happen? There would be a lot of energy associated with this electron that would be drifted from this end towards the drain end, okay. So what it would cause, this highly energetic electron may hit an atom, okay. When it would hit this atom, what it would cause? It would cause this atom to release an electron plus hole, okay. This electron would go into this drain, while as this hole is been attracted by the bulk of the semiconductor. It's been attracted by the bulk of this MOSFET, okay. So it goes into the bulk of this MOSFET. So due to this, what happens here? We do have, if the bulk is of somewhere lightly doped P, okay, here is the source which is of N type, here is the drain, here that's of N type. So holes are going this way, okay, holes are going this way, and due to this, what happens? The potential of this bulk increases. So when it increases, the voltage of this bulk with respect to source, that would be called as VSB, okay. It basically increases, okay. It increases as a whole, as the holes are being attracted towards it. When it increases, it here gives rise to a parasitic BJT, okay, due to which what happens? The electrons are being attracted in this way. So here is the BJT that attracts the electrons this way, okay. So this is only that I could just discuss about it. Yeah, here we do have another thing, that is hot carrier injection. Quickly, I would be also making a review of it. Hot carrier injection, once again, means that we do have an electron that's of having very high energy due to this high electric field, okay. So there is the possibility that it might hit this oxide layer, okay. So here we do have the gate oxide, so it may hit it, and it may just get totally, just it may intervene in it, and would penetrate in it basically, okay. So an electron might penetrate in it. So when a lot of electrons would penetrate in it, it would reduce its capacitance, okay. As we know, capacitance is equal to epsilon A by D. So this D would be reduced here, okay. So this D would be reduced, the quality of this oxide would be reduced. This is also known as the aging of transistor. It's called aging of transistor, okay. So when these electrons are being there in this layer, okay, and these are reducing this capacitance, what it causes the increase in threshold voltage, okay, increase in threshold voltage. So that means this time we would have to apply higher threshold voltage so as to cause the inversion there in the channel layer. So these were all about some short channel effects that we were going to discuss here, okay. Hopefully you would have understood it. Thank you so much.